Hello, math friends. This is AP Calculus Section 2.8 Day 1 Notes. Today we are going to be talking about the derivative itself being a function. So our working definition right now for the derivative of some function f at a fixed number a is f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. Hopefully you have that memorized by now. We've used it enough. But we can let the number a vary, right? In fact, a can be any x value, and we've already kind of done this in previous problems. But if we replace that a with x in our derivative equation, then we have this equation right here, which is essentially the exact same thing. It's just that it's f of x plus h minus f of x over h. And we think of this equation as being a function itself, okay? So given any number x for which this limit exists, we assign x to the number f prime of x. And so f prime of x is a new function called the derivative of f. The function f prime of x is called the derivative of f of x because it was derived from the function f of x. So basically what this is saying is if we have a function f of x and we find the derivative of the function using that highlighted equation, that our derivative itself is actually a new function that we could also graph and examine and look at. Let's take a look at example 1. It says use the given graph to estimate the value of each derivative and then sketch a graph of f prime of x. So on this graph right here, we are given f of x. And we're asked to find a bunch of slopes and then use those to sketch a graph of f prime of x. Because remember, when we are talking about derivatives, values of f prime of x are slopes on the graph of f of x. Okay, so we have our curve here, and I'm going to color it a little darker. This is our f of x. And we're asked to estimate some slopes. All right, so just working our way down the list. A f prime of -3. That's asking us when x is -3. I'm going to darken my axes quickly here just so that it's a little bit easier to count. All right. When x is -3, what is the slope on my function? So when x is -3, I'm looking at this spot right there on my curve. And it's definitely more shallow than a slope of -1, even more so than -1/2. I would maybe say that this is -1/4. It's a bit of an estimate, okay? When x is -2, right here, that's basically a little horizontal line segment right there. So I would say f prime of -2 is equal to 0. Again, we're looking at the slope at each of these x values on our curve. F prime of -1. So what is the slope right here when x is -1? Well, it looks to me like that's about a slope of 1. F prime of 0 right here, if we extended that line, I don't think that's quite 2. We'll maybe call that a slope of 1.5. F prime of 1, what's our slope right here? Well, that's a little shallower again. I would say that that's a slope of 1. F prime of 2, little spot again where we're horizontal, so that has a slope of 0. And then f prime of 3 definitely has a negative slope, but a very shallow negative slope. So we'll call that one -1/4 since we called that f of -3 -1/4. Those look like they're about the same. Okay, so this means that f prime of x has the following ordered pairs: -3, -1/4, -2, 0, -1, 1, 0, 1.5, 1, 1, 2, 0, and 3, -1/4. All right, so now if I want to sketch a graph of my derivative, a graph of f prime of x, I just need to plot those ordered pairs, and that is going to give me the function on my coordinate plane that's the derivative of f of x. So -3, switch colors here back to green, -3, -1/4, right there, -2, 0, -1, 1, 0, 1.5, 1, 1, 2, 0, and 3, -0.25. So my derivative ends up looking like a bell curve, basically. Okay, so that is how you find values of f prime of x using a graph of f of x. Sometimes when we're trying to sketch a derivative from an original function, we run into locations where our graph is not differentiable. The possibilities include sharp corners or kinks, jump discontinuities, or vertical tangents. And the following pictures illustrate this. In example A, we have a corner. In example B, we have what would be called a jump discontinuity, where we have this open circle and this closed circle. Again, left-hand limit and right-hand limit don't agree. And in letter C, we have this spot right here where basically our graph, the part of our graph has like a vertical line in it. And so we can't figure out the derivative at that point. So all three of these pictures represent places where slope cannot be measured or is undefined. Okay, so if we can't measure the slope, we can't find the derivative. If the slope is undefined, we can't find the derivative. So there are certainly locations on functions where a derivative would not exist based on these things. Our next examples give us three pictures of functions f of x, and from those functions, they're asking us to sketch the graphs of f prime of x. Notice that on the bottom, I wrote down three kind of bullets of information that I would consider to be really important things to think about. So right now, I might pause the video if I were you and write down those three pieces of information. When a graph is increasing, so from left to right, graph's going up, the derivative will be above 0. When a graph is decreasing, so from left to right, graph is going down, the derivative will be below 0. And then when our slope is steady, like when we have a slope of 1, think about a linear function where the slope is always steady. So when we have a steady slope anywhere on our curve, the derivative will be a horizontal line, because if the slope is always 1, then the derivative is always 1, which would be a horizontal line. So things to think about as you're taking a graph of f of x and you're trying to sketch from it the graph of f prime of x. Now, I'm going to tell you that I find these problems to be challenging, and I know that you will too initially, but the more you do them, the easier they get. So what I would do for the first example is I'm going to put some markings on my coordinate plane just to help me out a little bit. Some hash marks, if you will. All right, So if I'm trying to sketch my derivative, remember I am thinking about slope, right? So let's look at this parabola. First of all, the easiest spot to find slope is right here. You can see right here, slope is 0. Well, that means that the y value of my derivative is going to be 0 right there. Right here, when x is -1, it looks like my slope is positive and somewhat steep. I would say it's probably a slope of about 2. So when x is -1, the y value of my graph is going to be right here at 2, because we would say that this has a slope of 2. And then on the other side of the curve, that would have the opposite slope. So we would say that this has to have a slope of -2. So then the point on my derivative would be at 1, -2. So it looks like the derivative function to this parabola is going to be a straight line, or is going to be a linear function. And below here we can just write the 3 kind of slopes that we found. F prime of 0 was 0, f prime of -1 was 2, and f prime of +1 was -2. All right, looking at the second picture, notice that we have some kinks in this graph. And we just learned that wherever there is a kink, that is a location where our derivative does not exist. So right here and right here, we can safely say that our derivative does not exist. And then in the other parts of our graph, we have steady slopes. So first let's put some markings on our x-axis and our y-axis, just to make this a little bit easier for ourselves. Okay, now that I have that done, I would say that if, again, I'm looking at slope here, looks like the slope from -2 to -1 is steady, and it looks like I have a slope of about 2. I'm going up to right 1, so that's a slope of 2. So right here, I would say m equals 2, right? Then in the center, I have a steady slope here. Looks like my slope here is -2. And then here, from 1 to 2, again, it looks like my slope is +2. So remember, wherever your slope is steady, you are going to have horizontal line segments. Let's write some information down here. F prime of -2 was 2. F prime of -1, that's where we have that kink. So our derivative will be undefined there. F prime of 0, we have a slope of -2. F prime of 1, we have a kink again, so we will be undefined at that location. And then F prime of 2, we have a slope of 2. So if I'm going to sketch my derivative from x equals -2 to x equals -1, I have that steady slope, which is a slope of 2. So my y value of my derivative is going to be 2, but I'm going to have an open circle because it's undefined. And then that middle segment where my slope is -2 from -1 to +1, I'm going to have a horizontal line segment down here at -2. But again, I'm going to have open circles on both ends because I've got those kinks in my graph, and so I know that my derivative does not exist in those locations. And then finally, my last segment from x equals 1 to x equals 2 has a slope of +2 again. But derivative doesn't exist when x equals 1 because I have a kink in my graph, and then slope is steady from 1 to 2. So I will have a horizontal line segment there from 1 to 2. So my derivative there is the purple, and because of the nature of f of x, f prime of x is all horizontal line segments. My final example is probably the trickiest one. So let's put some hash marks on our graph. Okay, and let's look at some slopes on our curve. All right, right down here looks like our slope is basically at about 0. We'll call that almost -2. So we'll say f prime of -2 is 0. I'm going to write these down as I go because this one's a little trickier. And then when x is -1, f prime of -1 is about a slope of +1. Notice when x is 0, we have a vertical tangent in the center of our graph. So f prime of 0 is going to be undefined. What about when x is 1? And what about when x is 2? When x is 1, looks like our slope is about +1 again. It's kind of about the same as it was over here. And then when x is 2, we're back to horizontal, so a slope of 0. So now if I go ahead and I translate these into ordered pairs on my derivative, I have an ordered pair, -2, 0. I have an ordered pair, -1, 1. I'm undefined at 0. I have an ordered pair 1, 1. And I have an ordered pair 2, 0. Because of my vertical tangent, I know that my graph here, I know that it's going to continue to increase. But it's never going to cross that y-axis because my derivative does not exist when x equals 0. These are tricky and they take some practice. You have to think about where a derivative does not exist, and you have to think about the slopes of your lines becoming the y values of your derivative function. And if you think about where the graph is increasing, the derivative being above 0, where it's decreasing, the derivative being below 0, and where the slope is steady, the derivative being a horizontal line, if you check those 3 pieces of information and you examine the 3 derivative functions that we graphed, you'll see that those things hold true in all 3 cases. Example 3 asks us to first graph f of x equals sine x, and then from that curve, sketch a graph of its derivative. And when we do that, they're asking us to guess what the formula for the derivative of sine x might be based on the graph that we come up with. First, we are going to graph f of x equals sine x, and I'm just going to do 2 periods of the function. So from -2 pi to +2 pi. And we know that sine x has an amplitude of 1. So we can go ahead and we can sketch our function. Sine crosses the x-axis at 0, at pi, and at 2 pi. It has an amplitude of 1. At pi over 2, it's at +1, and at 3 pi over 2, it's at -1. So here is a sketch of 1 period of sine x. And then I can just go ahead and I can duplicate that over here from negative 2 pi to 0. All right, so here is f of x equals sine x. All right, so now let's find some slopes. And we're not going to be too crazy about this. We're just going to do the best that we can to estimate our slopes. So we're going to look at negative 2 pi, negative 3 pi over 2, negative pi, negative pi over 2, 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so I'm just going to work my way across the curve from the left-hand side to the right-hand side. So at negative 2 pi, and again, this is kind of a poor drawing, but you have to look at my scaling here. Looks like at negative 2 pi, my slope is about positive 1. At negative 3 pi over 2, my slope is 0. At negative pi, if the slope at negative 2 pi was positive 1, the slope at negative pi is going to be negative 1. At negative pi over 2, I have a slope of 0. And then this just keeps repeating. F prime of 0, that's going to be a slope of positive 1. F prime of pi over 2, my slope there is 0. F prime of pi is going to be negative 1. F prime of 3 pi over 2 is going to be 0. And then at 2 pi, I'm back to positive 1 again. So now I am going to take this information, which are going to be the ordered pairs, on my derivative graph. So now I'm going to sketch those. So again, this will be pi, 2 pi, negative 2 pi. This is positive 1, and this is negative 1. All right, so when I sketch this curve, I'm just plotting these slopes as ordered pairs. So this is going to be f prime of x, okay? When x is negative 2 pi, I have a value of 1, because that was my slope on f of x. When x is negative 3 pi over 2, I have a value of 0. When x is negative pi, I have a value of negative 1. When x is negative pi over 2, I have a value of 0. When x is 0, I have a value of 1. When x is pi over 2, 0. When x is pi, negative 1. When x is 3 pi over 2, 0. And when x is 2 pi, back to 1. So if I go ahead and I connect my dots, this should look familiar. Hopefully what you see is that f prime of x is a graph of cosine x. Remember, cosine is the cup, sine is the wave. So we just learned a very important piece of calculus information. The derivative of the function f of x equals sine x is cosine x. That's a very interesting relationship that we will learn more about later in the year. Our final example asks us to find the derivative of the function f of x using the definition of the derivative, and then state the domain of the original function and the domain of its derivative, and then we should use our graphing device to compare the graphs of the original function and of the derivative function, keeping in mind things we know about what our derivative should look like. All right, so let's begin with using the definition of the derivative to find the derivative of this function, which our working definition today is f prime of x, because the derivative itself is a function, is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. So that's what we're going to do right now to find the equation or the function that is our derivative. So f prime of x is going to be equal to the limit as h approaches 0 of f of x plus h. So I'm going to have x plus h, quantity cubed, minus x plus h, quantity squared, plus 2 times x plus h, minus, now I have to do f of x, so bracket x cubed minus x squared plus 2x. And this is all divided by h. All right, now it's algebra time. So I have the limit as h approaches 0 of, remember in yesterday's notes we wrote out what any binomial cubed is. So x plus h quantity cubed is going to be x cubed plus 3x squared h plus 3xh squared plus h cubed. And then x plus h squared is x squared plus 2xh plus h squared, but all three terms have to be made negative. So minus x squared minus 2xh minus h squared. Next, I distribute the 2, so plus 2x plus 2h, and then finally I distribute the negative to f of x, so negative x cubed, positive x squared, and negative 2x. You can see how easy it would be here to make one tiny sign error that messes up your entire problem. I cannot stress enough how important slow, careful algebra is anytime you are working with calculus. Slow, careful algebra. All right, now we get to cross out terms that cancel. So we've got a positive x cubed and a negative x cubed. We have a negative x squared and a positive x squared. We have a positive 2x and a negative 2x. And it looks like all of the remaining terms that we have in our numerator contain h. In my next step, I am going to factor out that h in each of those remaining terms. So I will be left with 3x squared plus 3xh plus h squared minus 2x minus h plus 2. And this is all divided by h. Good practice to check. I had 1, 2, 3, 4, 5, 6 terms left. I have 1, 2, 3, 4, 5, 6 terms in my parentheses. Just wanting to make sure that I'm doing good algebra and that I haven't missed anything. So now I can cancel out these h's and I can evaluate the limit when h is 0. So I have 3x squared plus 3x times 0 plus 0 squared minus 2x minus 0 plus 2. So these terms with zeros in them are all going to cancel, and I end up with my derivative function being equal to 3x squared minus 2x plus 2. So there is the equation for my derivative. All right, the next thing we're asked to do is state the domain of the original function f of x and state the domain of its derivative. Well, f of x up here is a cubic polynomial function. Polynomials have a domain of all reals. F prime of x is a quadratic polynomial function. Polynomials have a domain of all reals. So we can safely say that the domain of f of x is all reals, and the domain of f prime of x is all reals. And then the last thing they want us to do is use our graphing device to compare the graphs of f and f prime. So grab your graphing calculators. We're going to type in f of x, which is x cubed, so x caret 3, make sure you arrow out of your exponent, minus x squared plus 2x, and then arrow down to y2, and we're going to type in our derivative, which is 3x squared minus 2x plus 2. And I'm just going to do a zoom 6 on this standard window. And this looks exactly as I would have expected. We have our original function f of x in blue. That looks like a snake. It's a cubic polynomial. That's what it should look like. And then our derivative function f prime of x is red. It's a quadratic function and it looks like a polynomial. Some features that I want to point out to you, okay? Notice that our original function f of x is always increasing. From left to right, our graph is always going up, right? And notice that our derivative, f prime of x, always lives above 0. That's because f of x is always increasing, okay? Where our graph is increasing at a decreasing rate, so slopes are getting less, notice that our derivative is decreasing. When our slopes are increasing at an increasing rate, so from here moving up, our slopes are getting steeper on the blue graph, notice that my derivative is increasing. So the rate of change of your slope affects the positivity or negativity of the slope of your derivative. And that should make sense to you when you think about the fact that the derivative function is derived from the slopes of the original function. So let's go back to our notes. And on our notes here, let's just sketch a quick picture of what we saw on our graphing calculator. Here's our coordinate plane. Our original function f of x looked like a snake. And our derivative function, f prime of x, looked like a parabola. Both of these polynomial functions with a domain of all reals.